In this question, we have a parallel circuit. The first path of the parallel circuit is through the bottom path where current passes through the 6 ohm resistor and then goes back to the battery. The second path of this parallel circuit is through the top path where current flows past this parallel branch and then goes past the 4.5 ohm resistor before going back to the battery. So this is a giant parallel circuit. In part A, you are to calculate the resistance between X and Y. So we just focus our attention on this part of the circuit between X and Y. We see a 2 ohm resistor and a 6 ohm resistor connected in parallel. We can use the parallel resistance formula to get the resistance of this parallel branch to be 1.5 ohms. In part B, you are to calculate the resistance across the whole circuit. So if I redraw the circuit, we can see that there are two parallel paths. The bottom parallel path runs through a 6 ohm resistor, and the top parallel path contains a 1.5 ohm parallel branch with a 4.5 ohm resistor in series. Therefore, we can use the parallel resistance equation to determine the resistance of this parallel circuit. 1.5 ohm and 4.5 ohm resistors, when you add these two together, that will give you a parallel branch of 6 ohm. And the second parallel branch is a 6 ohm resistor by itself, and you can see the value over here. This is how we can get the effective resistance of 3 ohm. In this part, you are to determine the total current passing through the circuit, which is represented by ammeter A1. Since we have gotten the total resistance of the whole circuit in part B, and you know the EMF of the whole circuit, you can get the total current using Ohm's law on the whole circuit. Doing this, you will get a value of 4 amperes. In this part, you are to determine the voltage of the 4.5 ohm resistor. You have already figured out the resistance of the parallel branch in the earlier part to be 1.5 ohm. So we can use the potential divider equation, and when we plug in the respective resistance values, we can get a voltage reading of 9 volts. In this part, you are to determine the ammeter reading of A2, which is the current passing through the 2 ohm resistor. In the previous part, you have figured out the voltage across the 4.5 ohm resistor as shown here. So the voltage across this parallel branch, when you sum it up with the voltage across the 4.5 ohm resistor, they must give you back 12 volts. So we use this relationship to work out the voltage across this parallel branch to be 3 volts. So now we know for this 2 ohm resistor that the voltage across is 3 volts, the resistance is 2 ohm. We can then use Ohm's law to determine the current passing through the 2 ohm resistor. In this part, you are to connect a wire across X and Y to short circuit the parallel branch, and with that, what would be the new values for A1 and A2? So with the parallel branch being short-circuited, meaning all the current will pass through this new wire that you have just connected instead of passing through the 2 ohm or the 6 ohm resistor, effectively you are left with only 4.5 ohms in this parallel branch. We can determine the effective resistance of this whole circuit using the parallel resistance equation, and we'll get this value over here. With the total resistance known and the total voltage across the whole circuit to be 12 volts, we can use Ohm's law on the whole circuit to determine the total current passing through the circuit, and that is the value of A1. The current passing through A2 will be 0 amperes because all the current would have flown across the newly connected wire instead of passing through the 2 ohm resistor. And again, this is a case where we short circuit the parallel part of the circuit.